says 50.
Where?
On the homework sheet.
For today?
49 to 50 then.
That's okay. That just means.
Well, I'm really adamant about you doing 40 and 50.
Yes.
Okay.
You have 49 golden and then not golden.
Yeah, is that what
What did I
So
do?
do we have to do 49 or not?
Ooh, me too. Sure.
Oh.
So I made this out of my mind.
I even like counted the problems we had to do. I didn't even realize it
Okay.
was that's one.
The derivative. There are lots, well, there's not lots. There are a few synonyms for the derivative, okay? First question I have, what is a tangent line? Who can tell me? Oh gosh, you raise your hand at the same time. Pierce.
It's a line that touches another line once.
Okay, it's a line that touches once. Oh, here, I'll give it to you. Here you go. A line that touches, and I like that you say touches, okay, as opposed to intersects. I mean, it's intersecting, but touches once. Okay? So this is a tangent line. Okay. Tangent lines will be very important in this chapter. We will write the equations of tangent lines often. Okay? Well, what does that have to do with derivatives? Okay.
No, I don't.
I would like you to drop your pencils for a moment. We're just going to enjoy the show for a minute. Or two, or three, or four. Okay? Can you stay engaged without having your pencil writing? Can you do that? Can we focus? Okay. So, I will have you write this down in a little bit. But the derivative, we also call the instantaneous rate of change. And the instantaneous rate of change is what helps us figure out what the slope of the tangent line is. Okay? So derivative, I'll have you write it down later, is the instantaneous rate of change. Well, rate of change, we think of slope, right? Okay, well, instantaneous rate of change, instantaneous, okay? Slope of the tangent line at a point, okay? What kind of line do I have graphed right here? Is it a tangent line? No, it is a secant line. Very nice, Brandon, thank you. It is a secant line. And what I have x naught and x of 1, okay? And I have the limit as x of 1 approaches x of 0. And what does this look like? Looks like slope, right? Okay, so what's going to happen as I bring these two closer together? I'm getting closer and closer to that being a tangent line. So as we evaluate that limit, we're bringing those 2 points together to figure out the slope of that tangent line. Okay? What? You missed it?
No, I said I missed rise over
Oh. Now, let's just change the form a little bit. Does that look familiar? Yeah, the difference quotient, right? Okay, it's the same thing. It is rise over run, right? Our y value difference divided by Delta x, that's just the change in x. That's still like x minus x, right? We just wrote it different. And as the change in x goes to 0, what happens as the change in x goes to 0? It becomes a tangent line. So if we evaluate this limit and we take the slope and we make that delta x go to 0, what slope are we calculating? The tangent line slope, which I told you is a what? Derivative. Okay. Do I need to go through that again?
No, you're just so enthusiastic.
I love derivatives, Courtney.
I know.
Okay. So, this is the definition of the derivative. Pick up your pencil.
Yes.
We're screaming about
I know I'm not the only teacher who gets enthusiastic about their subject. And if I wasn't enthusiastic, that would be pretty boring for you.
It would be, I'm glad.
So make fun of me all you want, but I will not stop.
I had her 0 hour and she called me Danielle for 3 months.
Unit corrector?
I did every single day. I had her 0 hour, first class of the day, and she called me by the girl who sat there after me. For 3 months of class.
Oops. Okay, and notation here. Do you see that this is F and then like a tick mark? We say that this is F prime. That is the notation for derivative. So F prime of X means the derivative. Okay? And what I would also like you to write down is that a derivative is the slope of the tangent line, which we discussed, and the instantaneous rate of change at a given point. Okay? You will be asked, what is a derivative? How many things am I asking you to list?
2.
Every time. Full credit. Those 2 things. There are times where we will focus on the slope of the tangent line piece. There are times where we will focus on instantaneous rate of change. But I need you to understand that they both mean derivative. And we are finding the slope of the tangent line, or we are finding the instantaneous rate of change at that point. Okay, so very much like we did at the beginning of our limits unit, if you would like to change these to h's instead of delta x, I have no problem with that. Okay, do you remember when we did that?
Yeah.
Okay, so really, the algebra that we're going to go through today, you have already done in Unit 1. You just didn't know what you were finding. Okay, so now we're putting a different name on it. Okay, so here's our first example. Find the derivative of f of x equals x cubed plus 1. I know you know. Okay, don't start doing anything yet, please. I just want you to write this down, that this is what we're finding. Okay? It's not always about what the work is, but you also want to know what the original problem is. So find the derivative of f of x equals x cubed plus 1. So first of all, I want us to all get comfortable with f prime of x. That means derivative. Okay. And we get to do the limit as delta x approaches 0. I'm going to go ahead and use h's. Is that okay? That seemed to be what we were most comfortable with last time. F of x plus h minus f of x all over h. Please make sure you're plugging x plus h in to wherever there is an x. So since I have x cubed plus 1, we have x plus h cubed plus 1. Okay. Okay, and going back to all of our limit knowledge, if we try to plug in 0, we get 0 over 0. And so we need to do some algebra in order to get some things to cancel out. And you know, because you've done problems like this before, that what do we really need to get canceled out?
H.
That h needs to get canceled out somewhere. Okay? Now, from your knowledge of pre-calculus, you know that when you multiply x plus h, the quantity cubed, our coefficients are going to be
1, 3, 3,
1, 3, 3, 1 from our Pascal's triangle. If you don't remember that and don't think you can remember that, multiply out your binomials. You know how to do that. And don't forget that when we subtract a function, we subtract it in its entirety. Okay, what happens in our numerator?
The ones cancel.
Ones cancel. Anything else?
X cubed.
Our x cubes cancel. Okay. So now we have the limit as h approaches 0. Okay. Now I feel like we're all pretty good at algebra at this point. We've made it to calculus. Is there a GCF of our numerator?
Yes.
What is it? H. And what's in the denominator? So if we factor out an h of the numerator, it's going to cancel with this h right here. So we're left with 3x squared plus 3xh plus h squared. Can I go there? Is that okay? Do you agree with my algebra? Okay. So now we have a limit. I need to plug 0 in for h. So our derivative is 3x squared. Okay, Mrs. Holman, you told me that this stood for the instantaneous rate of change at a point. It stood for the tangent line at a point. You're giving me a quadratic. So what does that really mean? Okay. X cubed plus 1. Looks like this. Do you agree?
Mm-hmm.
Okay. So if I want, and we just figured out that f prime of x is 3x squared. We did all the algebra to get there. So if I wanted to know the instantaneous rate of change right here, then I could plug 1 into 3x squared, and that would give me the slope of that little tangent line. What is the slope of that tangent line? If I plug in 1, Okay, this would have a slope of 3.
Why do you put it 1?
I'm just saying if I wanted to know the slope of the tangent line at 1,
Oh.
we could plug in 1 to the derivative and know that that tangent line has a slope of 3 at 1. I just chose 1. Yes?
So will the derivative always have like an x value if it applies to like the whole thing?
I'm not going to say always because there could be a time, like if we have a linear equation, our slope is always the same in a line. So if a derivative describes the slope at any point, it's going to be the same everywhere. So besides a linear function, yes, your derivative should involve an x. Okay. If I wanted to know, here at -2, what is the slope of this tangent line? I could plug -2 in here, and what's the slope of that tangent line? 12. Okay, that is what it's representing. Okay, so it's going to be a function of some sort, but then we can take it and we can use it at different pieces to tell us something about our original function. Okay. Okay, now, what's nice, you've done this work before, so some of your homework will feel very review-like, okay? But just like when we talked in Unit 1, we had some vocabulary words that we needed to get in our tool belt, like continuity, a very important one, that appeared on your test. Let's talk about differentiability. So, first of all, differentiability. That's a lot of syllables. You done? Okay. Differentiability. Okay. A function is differentiable at a point if the derivative exists at a point. So as long as the derivative exists, we say that our function is differentiable there. A lot of da-da-da-da-da. What is our end time? Every Wednesday I have to get ready to clean. Okay, so the problem that we just did, we took x cubed plus 1, and our derivative was 3x squared. Can we plug any number into 3x squared? Any number, any real number. Okay, we have a derivative everywhere, so x cubed plus 1 is differentiable everywhere. It's not a problem because we have a derivative that exists everywhere. Okay? When are we not differentiable? Before I tell you the places where we would not be differentiable, I want you to have just a little discussion at your table. What would be cases, like some sort of either equation or graph, to where we wouldn't be able to have a derivative? Just think about anything. Think about Unit 1 stuff. Think about things you know about graphs. It's okay if you're wrong. I just want you to kind of talk. When would we not be able to find a derivative? Okay, I did hear a couple of things get thrown out that I like. Brayden, your table said something that I liked. Holes and asymptotes. Using calculus vocabulary, what could we say about holes and asymptotes? Those are where our function would not be continuous, okay? Which affects differentiability. You're good, you're good. Okay, so if we're not continuous, we might not be able to take a derivative, okay? Did anything else come up besides continuity?
I said if you have like an x and like a square root and you try to plug it in a negative.
Okay, so we have to make sure we stick to the domain of the function. I like it. Okay, we have to be careful with the domain. Okay. Celine, did you want to share your example?
Yeah, when I don't know how to call it, if like two functions fit together and they don't have the same slope at all.
Okay, so if like two piecewise functions are put together and where they're smashed together, their slopes don't look the same. Okay, very good. Did everyone hear that? So a piecewise function where the slopes aren't matching up. So this is what it looks like. So, non-differentiability. What most of you talked about. Points of discontinuity, holes, asymptotes, breaks. If we're not continuous, we cannot be differentiable. What?
It's gonna be what happens from
Oh, non-differentiability? Would you even be able to have enough tiles to do that?
I don't know, but if I do, I'd get a lot of points.
Something that did not come up in your discussion. Derivatives describe slopes. What kind of slopes are undefined? So if we have a vertical tangent line, we would say that we're not differentiable because technically that derivative is undefined. Does that make sense? If we're talking about the slope of a tangent line, and our tangent line has undefined slope, technically, like, you can't do that. So, not differentiable if we have horizontal tangents. And then what Celine was describing for us is like a piecewise function where our slopes aren't matching. I'm going to describe that as like a corner. Sometimes you'll hear it called a cusp. But there's no way for us at this point to describe what the slope is there. I could describe these slopes right here, and I could describe these slopes right here, right there. No way. Not differentiable. Okay. Bless you. Okay, so I want to talk about some of these graphs and how their derivatives relate, okay? So this could be another time where you just kind of like, we just kind of hang out and talk about it, okay? I wouldn't say that you have to write these things down. So here is a non-differentiable graph, okay? Heidi, which x value are we not differentiable at? At 0 because we have a corner, right? We have a corner. Not okay. Well, did you know? You don't. But did you know that if f of x is the absolute value of x, then the derivative is this. Oh, you have seen that. Max, what does this graph look like?
It's like kind of the same sort of looking.
Yep. Probably need it for your test. See? Okay. Well, at x equals 0, do you see any values on the derivative for x equals 0? Nope. It's because we're not differentiable, so it's not going to exist on our derivative. Okay? All right. Here is an example of a curve that has a vertical tangent line. Where do we have a vertical tangent line?
0.
At x equals 0. Okay. Fun fact. If our function is x to the 1/3, then our derivative is this. Not that you care, but it is. Well, where's our denominator 0 here? At 0. So in our derivative, we can't have a value at 0. If we have a vertical tangent line, our derivative isn't going to exist there. Okay. All right, now, how does, okay, we talked about 2 examples, right? Since we wrote down the 3. What was that third one that I haven't shown you? One slide for? Points of discontinuity. How do you think continuity and differentiability are related? Okay, you said something when we were talking about. I said, I was asking what's true about graphs that have poles and asymptotes. Everyone over here said they're not continuous, and you said they're not differentiable. Okay, so how does continuity affect differentiable? Okay, if they're not continuous, can we be differentiable? No. If our function is not continuous, then it's not differentiable. However, if it is continuous, does that automatically mean differentiable?
No.
Talk about it. Talk about it. Okay, so that was probably like the quickest reaction I've ever had to that question. Okay. So if we're continuous, does that mean differentiable? Who votes yes? Who votes no? Okay. Oh, and why no?
Because of the things we just went over, it could have vertical tangency, with vertical tangency or form.
Exactly. So this is true. If f is differentiable, boom, we know it has to be continuous. Fact. However, we cannot flip that because of what we just talked about. We can be continuous and still not differentiable. So it only works the one way. Okay? It's not an if and only if. Okay, there's some notation I want you to make sure that you have. Okay. F prime of x is not the only notation we have for derivative. Okay? So, if you have f derivative, I would write f prime of x. If you have y, you can write y prime. Those two both mean the same thing. White bride. Both mean derivative. This is funky. It's okay. So this means, hey, take the derivative with respect to x of this guy. Take the derivative with respect to x of what's inside. That's what that means. You're going to get used to it. It's going to be okay. Take the derivative with respect to x of this guy. And then dy dx. Very popular one. Dy dx. Okay, and let's talk about why this one kind of looks the way that it does. What did I tell you that a derivative is representing? Instantaneous rate of change. Slope of a tangent line. Okay? Well, let's go back to pre-algebra. How do we find slope? Okay, change in y over change in x, right? dy dx. Okay, so like we could write, change in y over change in x. You know where the d's come from? Okay, delta y, delta x. Okay. So all of those notations mean the same thing. Okay. Any questions about those? Okay. We're going to do one more example. Okay? And then that'll save us time tomorrow when we're going over our tests, which you're also excited for. Okay? All right. So I'm going to give you about 2 minutes. Go ahead and just write y equals x squared plus 1. And using the definition of the derivative, the limit of the difference quotient, I would like you to calculate the derivative. Using the limit of the difference quotient, I want you to calculate the derivative. Yes, it should involve an x at the end. Okay? Uh-huh. The limit as h approaches 0. I still gotta have u, okay? Okay. If you have an answer, compare it. If you're not the same, figure out what happened. Do you all have the same? Okay. Pod 5, do you all the same?
I don't think we're all there.
Do you all the same? 5, 1, 2. You still working? Oh, from here? Well, the h cancels out here too. So you should be left with 2x plus h. Okay, and then you can plug zeros.
So, is that, that's
Yep.
the first part?
Yep.
And then for the second part?
No.
We're not doing that yet.
We're doing it. Okay. So you should end up with 2x plus h to evaluate the limit of. And when you evaluate the limit, you should get 2x when you plug 0 in. Okay, so you can do a couple different things. So you can say dy dx evaluated at x equals 3. When we plug in 3, what do we get?
6.
And what does 6 mean?
It's the slope of the slope.
It's the slope of the tangent line, right? Why did I plug in 3?
That's the point you're doing it.
Because that's the point we're working with, right? So my tangent line okay, I'm going to ask that you use point slope form. And do you remember how I said, in calculus you don't need to simplify? Okay, so I'm trying to fit this all in, I'm sorry. Y minus y equals slope times x minus x. Boom, there's your tangent line. So we found the specific slope based on the point, and plugged it in, and that's our slope for the tangent line. End story. Okay? All right. Enjoy your day. Oh. If you are a homework hero, I forgot to hand out my candy yesterday. You can pick sour or normal, y'all. If you're a homework hero. Spears, are you not up there? Almost. Yeah.
I'm not up there.
There was one assignment there.
It was after
How do you know?
band. I think it was after the Titan Monarch game.
Yeah.
Yeah.
I just